Okay, so welcome everyone to this New Year sessions of the Young Researcher Seminars. We have today, as usual, two speakers, Gianmarco Perrupato and Mattia Ponte, in this order. So let me start introducing briefly Gianmarco. Gianmarco, he studied in Rome at the Sapienza University under the supervision of Giorgio Parisi and Federico Ricci Tersenghi. Then he got his PhD in the same university with the same advisors. And nowadays he is a postdoc of the Simons Foundation, still at Sapienza University. His main interests are in glasses, spin glasses, random graphs, and neural networks. Today he will give a talk whose title is Exact Dynamical Equations for Kinetically-Constrained Models. Please, Gianmarco, you can start.
So thank you, Federico, for the nice introduction. Can you hear me?
Yes.
Okay, I will share my screen. Okay. So can you see the screen?
Yes, yes.
Okay, nice. So thank you for inviting me to present my work here. I will talk about the mean field dynamics of the Fredrickson-Andersen model, which I studied with Tommaso Rizzo at Università La Sapienza in Rome. I will start with a brief introduction about the phenomenology of the FAM, and then I will move to its long-time dynamics. Well, the FAM model is between the simplest models, perhaps, of the liquid glass transition. It is a purely kinetic model in the sense that the Hamiltonian you see here does not contain interaction terms between the elementary degrees of freedom of the problem, which are Ising spins associated with the nodes of a given graph like this one. And what is non-trivial is the dynamics. We are interested in an equilibrium dynamics, which is kinetically constrained, meaning that at each step you pick a spin, sigma I, and then you suggest like a metropolis move, if and only if the so-called facilitation condition is fulfilled, namely at least f of the neighbors of spin sigma I should be pointing up. This definition comes from the attempt to mimic what happens in a supercooled liquid at a microscopic level, in particular the so-called cage effect. Indeed, the more motile, the motile regions, like this particle here in a supercooled liquid, has a rattling motion inside a cage, which is formed by its neighbors, surrounding neighbors. So the idea, so it is a constrained dynamics constrained by its neighborhood, and the idea is to think of spins pointing down like constraining spins, caging spins, and to the possible leaks in the cage, let's say, to spins pointing up. If there are enough leaks, you can think the inner spins to move farther. So the Hamiltonian that takes the form of an external homogeneous field in this notation tends to favor the spins to be down. So you may think that when you draw a low temperature configuration from the Boltzmann distribution, there could be spins which are frozen. Like in this case, you have this bidimensional grid with periodic boundary condition. The blue nodes are, the black nodes are spins pointing down, and the white ones are spins pointing up. If you evolve this initial configuration, you can clusterize the spins according to these three sets. You have the orange ones, which are spins which are always frozen down for all the times. The blue ones are frozen up, and the only spins which are, let's say, non-trivial are the green ones in this small square here. So if this happens, you have some degrees of freedom which are frozen. So it means that starting from a configuration, you may not be able to visit all the other configuration which are typical at that temperature. So you have an ergodicity breaking mechanism emerging from this facilitation dynamics. And what you typically do for studying this phenomenology is to give a look to the so-called persistence at a certain time t, phi of t, which counts the fraction of spins which are initialized down in the down state and persist in the down state up to time t. This quantity very depends on the behavior of this quantity depends on the graph on which the problem is defined. And since we want to learn something precise, analytical on this model, the natural choice is the so-called Bethe lattice, which is not a graph; it is an ensemble of graphs actually, and it can be defined as the uniform measure on the set of all graphs with a certain size n, such that each node on the graph has the same number set of neighbors. This ensemble enjoys the so-called locality-like property, which is if you draw a graph from this ensemble and you draw a node on the graph and you look at its neighborhood at a certain distance L, where L is a fixed number, doesn't depend on n, then this neighborhood is 3 almost surely when you take the large n limit. It does not contain loop. This allows for some analytical techniques like the cavity method to be used, and it's very important, as I will show you. So if you put an FAM on the Bethe lattice, you will find the typical mode coupling theory, mode coupling phenomenology. Namely, starting running a simulation at very high temperature, you will find that the phi of t, the persistence, goes to 0. This is the first curve on the left. If you lower the temperature more and more, at some point you will find that there's the usual two-step relaxation pattern emerging. So what has been, that is what happens, for example, in a p-spin model. So it has been shown by numerical studies by Sellito that this behavior, the end of the first drop that is called late beta regime, and the first the beginning of the second drop, which is the so-called early alpha regime, match very well the leading order prediction in the mode coupling theory. Moreover, this phi of t behaves very much like an ergodicity breaking parameter, because at a certain temperature, Tc, the phi of t doesn't go to 0 anymore, but it goes to a plateau with a power law behavior, this behavior here. And what you can do, interestingly enough, on the Bethe lattice, due to this locality-like property, you can compute analytically phi plat and Tc. Indeed, the observation is that a spin, in order to be frozen, requires at least k of its neighbors to be frozen, where k is very easily related with z and with f. So it is kind of a percolation problem. It's a modified percolation called bootstrap percolation, and this cluster satisfying this k constraint is called k-core. Having said that, it's very easy to compute self-consistently all the quantities, because you define the so-called cavity graph, which is, for example, this graph here. You pick a node, sigma 0, on your graph. You condition one of its neighbors, sigma r, to be pointing down, and then you can define the probability that sigma 0 is frozen in this conditioned cavity graph, phi c. Now, this example is for the case z equal to 4, f equal to 2. From the definition, you will find that in this case, in the condition graph, for sigma 0 to be frozen, there should be at least two of its unconditioned neighbors to be frozen. And then you obtain this equation that is giving you the first value of P, which is the Boltzmann factor associated with the probability of drawing a spin which points down, the first P at which you have a non-trivial value of phi C. And later, by merging Z branch cavity branches, you eventually can very easily find phi plat, which is the quantity we wanted to find with the critical temperature. So this was the behavior of the persistence at infinite times. At this point, we would like to understand what happens when the time is large but not infinite. So in order to do that, let me introduce some observables. The first one is the so-called block persistence, which differs from phi t because it doesn't count the spins which are persistent up to time t, but have been facilitated at some point, because this can happen. A spin can be facilitated, but maybe it doesn't flip. So we are not counting those cases in phi b. And from simulation, it is very clear that phi b and phi t have the same critical behavior, and their difference is very small. As I will show you later, is a small for our purposes quantity, and we will be able to neglect it. So the other two important quantities are these zero switch blocked persistence phi b 0 at time t, and this quantity counts the fraction of spins that have been blocked up to time t, as usual, but they have been blocked because the same 3 or 4 neighbors, because we are still in the, I'm giving an example for the case of z equal to 4 and f equal to 2. Well, we are requiring that the same 3 or 4 neighbors have been blocked in the down state up to time t. This can be represented by these diagrams. So on the left, you have a case, the continuous legs represent neighbors that have been blocked from the beginning to the end of time, while the dashed legs mean spins that can flip. So here you have these two cases, and we also want to define the one switch block persistence that counts all the events that satisfy these 3 requirements. So the first one is very simple. It's asking that there are 2 neighbors which are always blocked down up to time t. So you can see on the bottom these 2 continuous legs. Then the point 2 is you are requiring that there is 1 neighbor that was down up to time s, as you can see on the top right leg. And then it is free to, it can flip. And then you have another neighbor that is down from s prime, which is smaller than s, up to time t. So in this case, you see you have, so while in the first case you have the blocking set, the so-called the set of neighboring spin of the given spin, which block the spin is always the same. In this second case, you have 2 neighbors which are always blocked, which are always blocking, while you have 2 neighbors that switch from one another. At the beginning, the top right is blocking, then it is not blocking anymore, but there is the other one that becomes blocking in such a way as the given spin is always not facilitated, okay? So it is counted by the phi b t. Also phi b0 has the same critical behavior of phi t. So both phi b and phi b0 are proxy of phi t, as you can see in this plot again for Z4 F2. So what we can always do is to write phi b as the sum of phi b0 plus phi b1 plus an error. What's fundamental for our argument is that there actually is a hierarchy of contributions, as you can see in this log-log plot. So as I told you before, phi b0 decays as phi t. Phi b1 is smaller. This is again a log-log plot. It's smaller and it decays like phi squared, like 1 over t to the 2a. And the error is even smaller, 1 over t to the 3a. So we can do a perturbation theory. And in particular, you are allowed, if you go to very large t, to drop the error and also the difference between phi b and phi. If we do so, we can write a closed equation for phi t, as I will show you in a moment. Indeed, okay, we can start from phi b0. If we come back to our cavity graph in which sigma r is conditioned to be down, we can define the cavity persistence phi at a certain time t, which is the probability that spin sigma 0 persists down up to time t in the cavity graph, in this condition graph where sigma r is pointing down. If you can easily express phi b0 in terms of phi at via this equation, which is it looks very much like the equation we used to compute the plateau, but in this case you have the quantities that depend on t. At the leading order, this gives you exact the equation for the plateau. But now we want to go next to leading order. We want to keep this time dependence, and in order to do that, we need to estimate this phi b1. So again, for the case Z4 F2 in this example, you can okay. So for the case phi b1, as I told you before, we require two neighbors to persist down up to time t. So this contribution is given simply by the product of phi at on each leg. So is a phi at squared. This is very simply as before. Then you have P, that is the probability that the spin we are considering is initialized down. And then, okay, then you can observe that the probability that a permanent down cavity spin flips between a certain time s and s plus the s is exactly given by this derivative, minus the at in ds times ds. Well, it's clear because of course these are the only events contributing to the change of phi at. So this is exactly a derivative, and this gives you the second condition. This leg on the top right, you are requiring a spin to be blocked up to time s, and then to flip at time s. So you have this factor 2 given by number 2. And then you also have another requirement. You want the top left leg to have this shape here. Namely, you want this neighbor to be down from at least from S to T, at least from S to T. And this can be computed by invoking the reversibility of the dynamics. Indeed, if you have a certain ordered set of moves which are allowed by the facilitation, the reversed moves are allowed too. And therefore, we can say that this probability can be computed by starting here in the final configuration and coming back in time. Since we want this spin to be blocked at least from time s, because we are all interested that the spin we chose, this one, is never facilitated, this gives you a factor phi at of t minus s. You also have to subtract phi hat of t, because when s is equal to 0, this leg becomes completely dashed. This leg becomes completely continuous, and this contribution was already been counted by this diagram at the order before, in the slide before. So we put in relation phi b0 and phi b1 with phi hat. You can do exactly the same steps on the cavity graph for putting in relation phi b0 hat and phi b1 hat, the corresponding cavity observables on the cavity graph of these switch persistencies, and you obtain this closed equation for phi hat. That is exactly equal to the mode coupling theory equation, in which this delta phi, I forgot to write it, is the persistence, and it is subtracted the plateau value. So this quantity goes to 0 in the large time limit. So, for example, and sigma is the distance from the critical point. So with this observation, we have we have a prediction for the mode coupling theory parameter, for example, and yeah, in particular, if you put if you stay at the critical point where delta p is equal to 0, and if you plug these ansatz, these ansatz inside the MCT equation, you find a relation between lambda and a that gives you an estimate for a. Now, the Fredrickson-Andersen model is actually a family of models that depend on these two parameters, Z and F. And the previous argument apply to all these values. So you have a large set of predictions that you can compare with the analytical, with the numerical simulations. So this is what we found in the case of Z6, 5, and 4 with these facilitation values. And in the inset, you have this delta phi compared with the analytical behaviors, and you can see that that is pretty well reproduced. Then what you can do to do a finer check is to give a look to the logarithmic derivative of the delta phi, that when delta phi is equal to 0 should tend to a, which is the decaying exponent. Here we are plotting the error, the relative error of that we have at our times, simulation times on our data on this logarithmic derivative. And so what you can see is that the comparison is very delicate, because of course since we are looking at a power law decay, you of course have power law corrections, no? So you have to go very long times, and but if you go to very long times, since you are on a finite graph, you may start seeing deviation from field theory. So you have to increase the size of the graph. So at our point, we arrived up to this point. The dashed lines are guides for DI. That seems pretty, the data seem pretty reasonably extrapolate to 0. What you can test even more the theory, because the model I showed you before are this correspond to a discontinuous transition. Namely, there is this critical dynamical temperature at which there is the sudden appearance of a cluster of frozen spins, which has a finite size. But if you set f, the facilitation, equal to z minus 1, what you find is that the transition is continuous. So phi plot is equal to 0. In this case, simulation are nicer, even nicer. The difference with the discontinuous case is that in the discontinuous case, the persistence is proportional to the cavity persistence. Here I should have put delta and delta. While in the continuous case, the persistence is proportional to phi hat squared. So you actually, with the exponent A that you compute with the self-consistent equation for the cavity persistent I showed you before has to be multiplied by 2 for being compared with the data. And the comparison is pretty good. And a prediction is that this exponent does not depend on the connectivity Z. It is the same for all these models. And in this case, lambda is equal to 1/2, like in a p-spin model. So in a p-spin. So for the future, it will be nice to investigate more the nature of this hierarchy, and to eventually try to compute the correction delta phi, and try to apply this setting to other kinetically constrained models, and possibly to try to understand if it is doable to analyze the dynamics in a, let's say, static framework, just like in spin glass models. Okay, so thank you for your attention.
Thank you, Gianmarco, for the nice seminar, also for being in time. Is there any question from the audience? I don't see any raised hand. And maybe I can ask one. So sure. I understood that you made these calculations in a stationary state, isn't it? I mean, so is there the possibility to extend what you did to non-stationary states, like systems which are aging? If you prepare with the, I don't know, with the condition at high temperature, maybe then you lower the temperature.
What you can do is, for example, if you go below the transition point, when the system is well glass, either DCT is broken, you can study in the same cavity formalism, you can study the system at conditioning on the initial configuration. This, of course, due to the presence of these frozen spins, ends up in a measure which is not the trivial measure that I showed you before, in which the spins are factorized, but there are non-trivial correlations between the spins, which can be studied with the cavity method. And we are studying these correlations, and also possibly with the numerical simulations. Yes.
Okay, thank you. I don't see any raised hand. So if there are no more questions, we can move. Let's thanks again, Gianmarco.